Hello everyone. Good afternoon. Thank you for joining. So today it's my distinct pleasure to invite Professor Sumit Roy from the University of Washington. Professor Roy is with the Electrical and Computer Engineering Department here, where he held the ECE COE Integrated Systems Term Professorship from 2014 to 2019. Throughout his career, Professor Roy has made a significant contribution in the analysis, design, and prototyping of wireless communication and systems, and his expertise covers different technologies from 5G wireless LAN to vehicular network and dynamic spectrum access. In 2007, IEEE Communication Society recognized him as a fellow for his significant contribution in multi-user communication and the design of new wireless networking standards. He has garnered 10 US patents and also received a prestigious Barry Burton Best Paper Award from the IEEE Transactions on Aerospace and Electronic Systems for his work on radar Wi-Fi. Professor Roy currently represents US on the NATO SET 302 technical working group for cognitive radar. And he has worked on many different companies. He was at Intel's Wireless Technology Lab, Microsoft Research, and several others academia group. And he has served in a various role for several technical standardization, especially IEEE Future Networks Technical Committee. Most recently, between 2020 to 2022, he served as the program lead for Innovate Beyond 5G within Department of Defense. And let me just tell you, these are only a few brief points I want to mention, and it's kind of an abridged version from his long and illustrious career. So with that, please join me in welcoming Professor Sumit Roy.
Thank you. So my first time here, actually the first time in the state of
South Carolina.
South Carolina.
Okay.
So good to be here. Thank you for coming. So what I wanted to do today is a bit different, as Sanjeev's mentioned. I'm sort of more of a core wireless person. My training is more or less standard communications and signal processing and networking. This is you might have heard in the context of 5G or beyond 5G or 6G, one of the key thematic technologies, or one of the key thematic pathways to which technologies converge, is by integrating sensing, traditional sensing with traditional comms. And the reason is, for those of you who are not expert in the field, is not too hard to understand, right? If you look at how communication technologies, either your phone or Wi-Fi, how they evolve based on one thing: how much can you eat? It's based on throughput, right? So if you took a communication theory class, in your communication class, the first thing they would tell you, how do I increase data rate? Increase the channelization, increase speed, right? So if I increase bandwidth, you study some basic, I can get more data. Also, that's not the only way. You have things like MIMO and all of these other technologies which have matured with typically 4G to further increase the data rate. But increasing bandwidth and increasing modulator encoding, all the other things, plus multiple access, go into the cooking of, and increasing, data rate and throughput. Look at it from a sensor perspective. What does radar do? Radar stands for radio detection localization, right? It gets you accurate ranging as well as dopping. How do you get accurate ranging? The radar uses a large, right? So as a matter of fact, the overview of this picture is that the future which is already here. So you all know that every vehicle manufacturer has two things, right? Electric vehicles as well as automotive, right? Everyone. Now, a typical vehicle, particularly perspective of integrating automation in vehicles, will have lots of sensors in it. Traditionally, cameras as well as if you've gone to the Bay Area and you've seen, Google car or Waymo's car or any of these, multiple companies running automated, the Google car has been running in the Bay Area for 15 years, right? And now there are multiple companies, small startups and others, which also have licenses to give a driverless. So basically, think Uber without the driver. There are already trials running around in San Francisco where you can order, within very specified city limits, a driverless. And so such cars will be equipped not just with cameras, but in the case of the Google car, there's the famous LiDAR, or as an alternative, multiple radars, right? And so the reason is, this is very interesting to me personally, because I was mentioning to Professor Sur that my PhD thesis 30 years ago was actually on tracking and estimation for radars, but it wasn't this radar. It's the radar that you see when you go to the airport, okay? Which is the big radar, long range, right? And there was interesting radars. If you were an electrical engineer 30 years ago, that would be one of the more interesting technologies. And it died out. Electrical engineering, we don't teach radars or detection estimation of how radar targets work anymore so far, because you had matured, it wasn't a commercial thing till this happened. So this is literally like the rebirth of radar, but this is commercial radar, low power, shorter range relative to how, a weather radar or an air traffic control radar operates, right? So what I'm going to try to talk about today is sensing using radars, but from my communications perspective, because as you will see today for those looking ahead, this integration of sensing and comms, there are various acronyms, ISAC, integration, sensing and comms, or joint communications and sensing, is one of the key themes in 6G. And what that means is that we have historically thought about the radio and the radar or sensors like radars as two separate techniques. But increasingly, as these parameters like bandwidth and power come together, they can be thought of being integrated. Either the front end could be shared, it's not the front end. Maybe the front end is not shared because the bands may be different. But certainly the back end, the digital back end can be shared. So there are many, many interesting reasons why these techniques can be quote unquote integrated. And certainly the operational logic, once you have signals, which are comm signals, so whether it's a Wi-Fi or 5G signal and a radar signal, to what purpose can you put them jointly to use? And that is also from an application perspective not that difficult to understand. In many, many communication applications, you do want to know location. If I know the location of an object, I can say direct beams or direct power to that object, right? And get more throughput to it. So if you look at MIMO, if you have a Wi-Fi access point, if you look at it with multiple antennas, it has, one of the key features from cellular, whether it's Wi-Fi or both Wi-Fi and mobile is both cellular technologies, is the ability to use MIMO to direct beams to specific users. Well, how do you direct a beam to a specific user? It is best done when I know what the user is, right? So if I know the location, both in range and in angle, right? These are largely static users, so I can do better comms. So sensing can aid comms. Conversely, comms can aid sensing. That's a different use case. It's distributed radars, MIMO radars, some here. So the point is the convergence of comms and sensors, of technologies we have thought about separately, is now, based in sort of the foreseeable. Yeah. So that's the perspective. Okay, so I'm going to talk about some work from my two recent PhD students. They have graduated. Actually, one of them is a MathWorks responsible for one of the radar tool sets as a result of it. And the other is at one of these startups in the Bay Area, which is running, autonomous vehicles. So this is just to give you a sense of where, if you do work of this kind, where you might end up with in terms of jobs. All right. So let me say this. This is something I'm going to go over this quickly because Professor Sur's lab, you don't have to look at my site, you have to go on to his lab and see a lot of this. So TI, for those of you who don't know, right, it got out of the DSP business. You know, when I was growing up, you had TI TMS 320C, which you program. You don't see that anymore. They got rid of the DSP business, and they basically they did a hard pivot to this use case. And it sells. This is one of the major seller products, right? Radar, okay, which we all can use, and he has it, and I have it in my lab, and you can see this, right? So I don't know. I don't know. Are people familiar with? I have a few radar signal processing slides. I don't know how much of that I should go into.
You can go into as much detail as you can.
Okay. So I'm going to. So this is what a board looks like. There's a daughter board and a motherboard. That's typically, there's this family of the AWR family, right? And it has a transmitter, it has a receiver, it has ARM processors, it has DSP, so they compute, right? And the important thing is this. These radars operate, it uses these 4 gigahertz of bandwidth in the 77 to 81. It's unlicensed band, which you can use, right? It can support MIMO. I mentioned this, but limited MIMO, right? Okay. And I mentioned to you the processors. Right. Now, I'm going to skip over this quickly. All right. So I just said that what we are talking about, MIMO is multiple input, multiple output. So it's simply having physical antennas on 2 sides of a link. So just to go from the perspective of communications theory, one of the biggest advances that happened with say 4G. So if you go around town and look at the base station, you will see a tower with antennas. Now, from long ago, antennas were sectors. They basically took a 360 degree for coverage. They had 3 120 degrees. That's not my. You'll see multiple antennas, all in the same band, and they use collaboratively to increase the data rate down to this. So one of the major advances in the 90s in communication theory, which actually technology is, so 2 things. You must have multiple antennas on the base station side, and you must have multiple antennas on your form. So obviously on the base station side, you can put many more antennas because of form factor. Here you have more limit. So a better example is go stare at the AP hanging upside down, a Wi-Fi AP. You typically see 4 dipole-like antennas. And if you have say 2 antennas on such a device, you can double your data rate relative to not having 2 antennas. Okay, so MIMO is one of these big wins in terms of technology that has infiltrated both cellular as well as Wi-Fi. Okay? As a matter of fact, the degrees of MIMO, so these days, if you look at research, it's all called massive MIMO. So the degrees of MIMO has actually proliferated. So having 4 and 8 antennas is called like, kids MIMO. So today, if you go to massive MIMO, a number to think about is like 64, phased array with 64 elements or 5. Okay? So here, this radar has got sort of baby, right? So it does not match the MIMO with comms. But this is the trend. So okay, so this is, I'll just say this, right? So you can look at what's on Waymo with Cruise. Cruise is another of these companies, run this car companies, and sort of the hardware. I'll skip this, right? So what I'm trying to do today, I'm trying to cover a lot. So I'm going to talk about two things. The first is multi-radar coexistence. This is a bit of an academic problem currently, but it is exactly one of those sort of foresights, leap ahead problems, which will occur for radar manufacturers if you don't solve it. I'll explain to you why and why you need to look at this problem. Why it has to be addressed in design and standards. The second is much more of sort of using radar vision or computer vision, right? But on a vehicular platform, right? In order to do, what you would call scene or object recognition, right? So the second is a much more standardized thing, but I will give my take, i.e. my students' approaches to how to improve, the same. Right? So there are 2 different things. I'll go over the first quickly. So the first one is about multi-radar coexistence. And here's the point. If in the future, every car has one of these radars, actually, as I showed you, multiple such radars. So just to give you sort of from a systems perspective, a car, these are called ADAS, Advanced Driver Assistance Systems, right? That's the terminology that the vehicle companies use to do. So what is the driver assistance? If you think about it, and you see this in TV ads already, right? Parking, lane change, they call lane assist, right? Anti-collision, right? That's what you usually get the beep, 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 when you're backing up, all of this. Right? So you will have forward-looking radars, short range. You may have, as in the first slide, a much more longer range radar to do sort of, cruise control, right? Or advanced detection, right? From a car way ahead, which may detect that there is some incident occurred, etc. You have side-looking radars for lane change and for side collision control. So cars will have sort of multiple radars. That's the thing. And now, if you imagine, at lunchtime, 8 o'clock commute time, 5 p.m., you're at some downtown, crossroads. Lots of cars parked. Each of them have radars which are chattering. So the point is this, that when in sensing, people only think that you have a sensor, and the sensor. So what is the radar's job description? The radar, here's a car, here's somebody in a pedestrian in a crosswalk. This is the desired target for that radar. So you know what a radar does? It sends when it's an active device, it sends a pulse, it sends the backscatter, it does some processing in order to detect, localize, when I say localize in distance, relative distance in range as well as in velocity, right? But so is everybody else trying to do the same thing, right? So if you have lots of cars in the neighborhood, okay, everybody has a radar, and you have not planned for the fact that everybody else is trying to do the same thing, then if you look at, this is what we traditionally in networking, we call them multiple access. That means the signal from here into the receiver, right, causes interference. And as a matter of fact, since this is one way, the interference is stronger typically than the backscatter, which is your desired signal. So, in signal processing terms, it's a low SINR or a low SIR problem, right? Which is where most of you are on your teeth because it's harder, it's more challenging, right? So essentially what's happened is that nobody's looking at this problem right now, right? Because, you use the radar in the lab, there are no 5 radars operating simultaneously in that same 77 to 81 gigahertz. So this is a foreseeable problem that in networking, in wireless networking, how do we solve it? We solve it by design of multiple access. So if you study Wi-Fi, it has a protocol called CSMA, carrier sense multiple access with collision avoidance. If you study Ethernet, you study a protocol called CSMA, right? Where you have a shared channel, 77 to 81 gigahertz. If many people want to use it, you must have some rules of how people use it, right? So right now, the sensor, the radar designers haven't thought of this, but this is an obvious problem. Yeah. So that's why I say it's an academic problem right now, but about to be real. So yes, please.
So can the signal be slightly modulated?
So this is all modulated, by the way. So let me tell you what the radar signal is. Okay? So by the way, so then I'll go to the second thing later on, which is about radar vision, right? And this is perhaps more traditional chronology, but it'll have my spin on it. All right. So the radar is a chirp, is a frequency modulated continuous. So, if you've studied radar, so none of this is new, this FMCW radars have existed since 1950s. Except that this is a low power, short, medium range. So these are modulated, right? So if you look at, I'll show you this, all right? Let me show you this. This is what a radar chirp signal looks like. For those of basic signal processing class, you can see the amplitude versus time slope. So it's a linear frequency, swept frequency slope. So frequency versus time, you see this line in signal versus time. You can see that you're going from lower frequency to higher. Okay. And so all of you know, if you take the Fourier transform of it, you literally will get approximately a boxcar flat spectrum, right? Over 77 to 80. Okay? So every radar is sending out such a signal. And you can ask, what can we do? Is that your sense that what can we do to this modulation in order to allow multiple people to transmit? That's exactly the question, right? So in communications, we have figured this out, how to allow people with their coding, like in CDMA, the code division multiplexers, to let people access the same channel simultaneously. And the point is, similar such ideas need to come to radar. Yeah.
I have a really basic question. So you mentioned LiDAR. My understanding is that these devices like LiDAR are developed so because they suffer maybe lesser problems than radar. So to what extent is for localization of objects? So to what extent is the solution for say an application like autonomous driving moving towards better such devices rather than trying to make multiple radars coexist?
Yeah, so it's a so I'm not an so let me say this. If you go, as I said, if you go to the Google car, many, even Tesla, Musk, so he's a camera guy, the Google car has a LiDAR, right? So there are various opinions as to what technology, suffices for, your application, which is autonomous driving. So a LiDAR first is right now even several $1,000s, significantly more expensive than some of these radars. One, so there's a cost factor. But then as always, when you pay something, you expect something more for it. So a LiDAR, its resolution, its point cloud is much better, than what a radar provides. Okay? So there's a trade-off. So here's the point, right? That why do some companies? So there's some companies who don't use a LiDAR but use a radar, and they may use multiple radars because they feel that with the appropriate signal processing and ML and so on and so forth, they can get most of the performance that they would get with a LiDAR. Now, of course, the LiDAR community is not static. That cost is also coming down, et cetera, et cetera. So, it's a healthy competition between technologies for that. Okay. But, I think for us, like in a prototype, this thing is cheaper and easier to get radars than get a LiDAR. Right? Okay. All right. So was that the question that you're asking? So essentially, these are all modulated signals, right? And you can encode them in order to do multiple access. And actually, that's the short theme of my work, that nobody has yet looked at how to do this. So if you have heard of SPEC CDMA, that's one of the technologies underlying multiple access. That's what you do. You can have multiple people use a spectrum, a band, at the same time by giving people different codes. So you can have orthogonal access in different ways, and the whole point is this. One sentence. Communications, networking people over 50 years have worked on this multiple access problem. Radar people have worked on this for 0 years. Take that knowledge and stick it into radars, right? And you are going to need some ideas like that to solve the radar multiple access problem because it's coming, right? You have to, so basically whatever vision problem you're solving now, you have to solve when there's lots of interference, right? Nobody, if you look at any papers, nobody's solving the vision problem when you have a lot of interference from other areas. So short problem statement. Okay. All right, so this, and you can see why, as I said, why it's a low SIR scenario, because your desired signal is backscattered. And any of you have done a bit of radar theory, right? They receive signal from backscatter because there was called the radar cross section, which is highly dependent on the target geometry. And also, there is two-way propagation. This is only one-way propagation. So it is a challenge. And now the sum of the interference, depending on how many other such radars there are, further lowers the signal to interference ratio. Okay, so this is not so anyway. So the whole point is this, just to give you just a very quick overview. Suppose this is what's on one of these blocks, right? You have an antenna. You have what's called a duplexer. This is your source transmitter of this FMCW signal. You send it out. You get the desired signal back. So the blue is the desired signal. And how does a radar process the FMCW return? You basically take your reference signal, pass it, you mix it, you down convert it into IF, and then you do some processing, and then you declare detection. So if you look at this, what happens is this. You have your desired signal now in the presence of it. The red is the background, the interferer. The blue is, your desired signal. What happens is this, that the output of this, IF or low pass filter, you now get two actors. So it's not that difficult for you, for those of you just do a bit of radar signal processing. But the reason that you did this chirp is, so you send a chirp out, you get a delayed chirp. If I mix the two, then the delay is proportional to the beat frequency. Okay, fairly simple physics. And the beat frequency is this blue, right? Okay, so what you're expecting is I have one target, I should get one echo, right? But now I got two. Now, so remember, I color coded it. Suppose I didn't color code it. Now I get two returns. Which one is my target? Which one is what I call a false target or ghost? A ghost, whenever you see this, is it something masquerading as a target? It's in my, you see what bandwidth, right? So you can see what the issue is, right? As you have more and more of these, interference, you're going to see. So essentially, if I just skip forward, just to give you an idea, the impact of radar interference is kind of twofold. And by the way, this example is a very simple example, sort of homework in undergraduate class, is to show you that if the source and the interference are coherent, you will get this. So if you look at it, this is the desired target. I sort of mixed up the color coding, should have been blue. The desired target is here, and the undesired is there. Both of them give echoes, if they are coherent. Obviously, the interference is there, different sources not coherent with you, right? So if you don't have coherence, what you see is a noise floor. So if you have an incoherent interference, so you get one of two things. The more coherent you get this target, false targets, right? The less coherent it is, your noise floor rises. Okay, so basically your interference gets treated as noise, but you still have a problem. Okay, depending on how much the noise flow, right? So you can run this in MATLAB. These are all sort of in MATLAB using toolboxes. You can run this, and you can get a sense of what does interference do to the port detection. Right? So that's what I was trying to. Yeah. So now, again, if you run this thing through, what happens is, so increasingly, in the rest of my slides, you will see this. Okay, so first of all, you can see, as I said, after this IF or low pass filtering step, you have ADC, you digitize it, and then always you do FFTs, or GFTs. The first FFT is for range, okay? A second FFT is for Doppler or velocity, right? And then you get these 2D plots, right? So, traditional radar signal processing creates these 2D plots, and then if you repeat it, you can get a third dimension, which is time, right? So these are sort of, short-term, Fourier transforms. You get 2D. And now you can see you have two targets, right? Except that I color coded and I told you one was a target. And sorry, this was the target, this is the ghost, right? But after you don't know, right? Which is ghost. Okay. All right. Or you might get based on something different. Maybe if these two are so this is a very simple example. You can see these two quote unquote the two targets are well separated in speed as well as in range. Right? Now you can imagine if they have the same speed, right? Relative speed, then they will align like this. If they are the same range, they will align horizontally. And if they have the both same speed and same range, you have no discrimination. You will not see two, you will only see one. But they are close enough to each other, the side lobes of one will solve it. So you can start seeing from a signal processing perspective what the issue with this, the traditional radar processing is. Anyway, so as I said, you do a range DFT, you do a velocity DFT, right? Now, you can now imagine, although, we are in an era of AI ML, everybody wants to do an ML. So I just told you what the problems with the traditional, signal processing detectors. And now you can start thinking, with other side information, etc. What other non-traditional, what can I do to fundamentally improve this radar detection in the presence of multiple sources? I'll just leave you with this. So the design goal is really, so So what is false alarm? Anybody know what a false alarm is? And you must, any of you do this work. I think even in sort of computer vision, you have this notion of error of the first type or error of the second type, right? An object is there and you miss it, that's one type of error. An object is not there and you declare it, that's the second type of error. So the false alarm is the object is not there and you declare it. It's one of those types of errors, right? And so what happens is this, that let's say that, you're only looking for one target, right? But you get an additional ghost false target, right? What will happen is, if you don't have any other information, I will say that there are two targets here, right? So the second one is a false. Right? And you really want not to be able, at the end stage of your processor, you want to be able to filter out these things, right? You do not want to declare these as desired targets, right? So you want to be able to, so essentially this is a classification problem. This is the desired, the rest are undesired. I want to get rid of them. So you can now think that, now you're going into much more non-traditional sort of, process. Okay. So what I was going to do is this. So I'm just going to give you a hint, which goes to how do you suppress these false alarms through that signal design. At the end of the day, that's what it is, right? That instead of having pure FMCW, can I do something to this the chirp in order to have multiple people still transmit together, and yet a detector is able to get the target that it wants and filter out all color. And so, as I said, for those of you who are in communications, this is well understood from 50 years because we've been doing this for a very long time. The census people should get wise and adopt that knowledge and basically adopt and adapt. I don't say adopt. You always there's some adaptation. There's always something you do. So just let me tell you how to do a simple simulation study. What you can do is simulate using MATLAB, take a road and drop multiple cars, or take a unit circle if it's a 1D simulation or a 2D simulation. And here's what you do: you give everybody so you drop nodes, vehicles with each radar equipped with some random Poisson process. The details of this are not, right? So these are all randomly placed, right? And then they all transmit these radar pulses, right? In the same band simultaneously, right? And now what you want to look at this is that what is the pattern of interference at a victim radar, correct? All right. And now what I'm going to do is this. I'm now going to specify that each of these stars which are transmitting, this is what we call random frequency division multiplex, right? So it's just frequency division multiplexing, but randomized. Right? So you know what frequency division multiplexing is? That if you get this band 77 to 81, I can subdivide it, and then I can ask one radar to pick one of those M. So we will use the terminology M subdivisions of the bit, right? And I can I can ask everybody to pick one of these subbands randomly, right? Somebody else picks another, again, picks independently one of those M subbands, right? So you can get some anti-collision as you can pick, right? People are not everybody is going to pick that same band, right? And so how does this work? So what I was going to say, so basically, so the whole idea is this: on the y-axis are subbands. Y-axis are subbands, and there's a whole bunch of radars. Each of them picks their subband. So here I showed that two radars pick the same subband, right? But the third radar would have picked, subband 2, and the fourth radar may have picked subband 3, jump, right? So is it clear what random frequency division multiplexer is? You get a full band. I'm going to divide it into n subpieces. And by design, I'm going to randomly allocate a subband to each one of them. And all the radars are sent a chirp on that subband. So you're not using the full band. Let's say, so if I divide 4 gig into 4 1 gig subbands, you only transmit on 1 gig subband, right? Yeah, but then whoever is orthogonal, I don't do them, right? So this is very standard. This is randomized. So, and the whole point is this: if you define a notion of capacity, so the capacity is roughly for you. Now, by this method, how many such multiple radars can transmit, right? With this random, allocation, and yet get very good detection performance, right? It has no false, that false alarm problem that I mentioned, right? Guess what? Have any of you seen these curves? So this is a capacity curve versus the density, which is the number of such stations per unit. There's a student, I've been seeing this in your computer networking problem class, which
Traditional queuing kind of.
so this is basically if you studied Aloha. Anybody know? So if you take his computer networking class, at some point, you will see this curve. For the capacity, what's called Aloha slotted Aloha. So what I just told you, I made a long story, but if you don't think about it, this random access I told you is like slotted Aloha or unslotted Aloha random access. So you know what slotted or unslotted Aloha is. Okay? It's very similar to this. The point is this: the capacity first increases with lambda and then get killed by that exponential. So if you look at it, this is C versus lambda. So it looks like lambda e to the minus constant times. So for low lambdas, what happens is you get this gain. So if you have not too many cars and you have m, but there's also a term m. So actually, in our textbooks, we only do single channel Aloha, right? This is the multi-channel Aloha. So actually, if you look at it, there were some papers written around the same time that if you had the Ethernet with multiple channels, then you can divide the traffic. This would be the expression. So this would be a multi-channel version of the standard channel Aloha. But the idea is not that, for those who are not experts, it's not that deep. In the beginning, when you have large enough M, by randomizing, you get a benefit. You're getting de-confliction. But as lambda increases and M is fixed, right? You're going to still get killed by the increasing number of collisions, because in any subband, there'll still be a lot of people who are, right? So it goes up first. And then, so if you look at this, so well, this one has other curves. So if you look at this, this is the C curve. So actually, this, so on the same scale, it doesn't show, but it just goes up. So actually, if you just draw this, it still goes up and then comes down. But on the scale here, it looks. So the whole idea of this work was to show that you don't do Aloha with not too much thought. You can do way better than Aloha, which is not a great fact because we have known this, right?
Yeah. Is the performance normalized with respect to the bandwidth? Like lower bandwidth will give you lower resolution, so capacity.
But here we are. So great point, right? So here we are assuming that 1 gigahertz bandwidth, suffices for. So we are able to, so, you're right. Normally you would lose on the, obviously lose on the resolution. The resolution. Yeah. So here is we are saying that going from 4 to 1, you still are, you are over provision on the resolution side. Yeah, there's no free lunch, of course. Yeah. Well point. Right? So here we were just saying that how could you trade off, right? The number of simultaneous, radars, which can then go ahead at 1 gig resolution, rather than say having one guy which needs, 140, right? All right. So I'll just say this quickly. So you can't see this result because this result is right here. It looks like this on the scale, right? So what are all these other two methods? These other two methods are actually also very well known to communications people. And I'll just tell you one of them and then leave. Leave this topic, which is do frequency hopping. So again, many of you might have known from communication, there's spread spectrum and CDMA version, the frequency hopping. So what's the difference between frequency division multiplexing and frequency hopping? You can see this. All right. So first of all, we go back to, I didn't emphasize this. The radar sends a chirp, which is a linear frequency signal. Each chirp is just give you some numbers, few microseconds, right? And it sends a sequence of chirps. Let's say, back to back, maybe 100. So maybe, or 10, somewhere between 10 and 100. So it's all the order of 10 to 100 microseconds, right? And then it repeats, okay? Maybe it repeats every millisecond, right? So roughly these numbers, right? So this is one chirp, right? Okay. And then the whole idea of frequency hopping is every time it sends a chirp, you can hop. And when I say it sends a chirp, this is a frame of chirps. This is not one single LFM. It's that 10 repeated. So after every frame, it hops. Okay, so you have more randomization, right? And that works way better than I pick one, band randomly, but then stay on it. So that's where you get these capacities. And then if I do some further coding, PCs, phase coding, etc., if I'm able to do phase modulation and actually capture the phase, I can do it. Right? So what I'm going to do is I'm going to leave this topic to see. My whole point here was that this is a, I don't know, forthcoming challenge. No sensor designer currently, the radar designer works for this problem, but you can see this without much listening that if you have, you will be a victim of your own successes. They say, beware what you wish for. This is what you're wishing for. And you have to change the radar, the radar design to include concepts of multiple axes. Okay. So that's the problem. All right, so I'll skip this. That's all. I think much of this I know. So we have papers. This is derived, published, etc. Okay, so all right. Now, in the second, let me talk about. So this is back to sort of using traditionally radar for vision, right? And so one of the things we know is that why do we use radar fundamentally or these lidars as an assist or as a complement to the cameras? As we all know, you've taken pictures when you have poor lighting, etc. Your camera just right. So the whole idea of any of these other sensors would be to complement, right? Your visual, your the visual items, right? And so, so a radar or lidar is much more robust to environmental conditions like fog, snow, all of this rain, whatever, and etc. There's a large bandwidth, obviously, 4 gigahertz, an immense amount of bandwidth available, right? However, no free lunch, 4 gigahertz. If you want to sample 4 gigahertz, you need, giga samples per second in order to process that 4 gigahertz, right? Great thing is, band, resolution, range resolution, order of centimeters, and Doppler resolution fabulous because of this bandwidth. Okay. So as I said, I think to your question that the push to FMCW radar is seen as a low-cost substitute, but there's performance trade-offs. And the idea is to see how much with this low-cost substitute, but with smarter processing, can you reach a LiDAR types solution. Okay. All right. So now, major cons with the radar angle resolution. Okay. So as I mentioned to you, angle resolution really requires a large aperture, either physical or virtual. So basically, when I say angle, it is you're looking at and so you need azimuth. You need to see the next phase, right? So as a matter of fact, the base that AWR 1642 family radar front-looking, angular azimuth resolution is the order of 15 degrees or so. With 15 degrees, you cannot discriminate. You look ahead, car ahead, and the car next, right? And the elevation is even worse. When do you need elevation? You're going under underpass, bridges, etc., right? Then you need elevation. So you certainly need azimuth. And in many situations, you need elevation. That's the weakness, because now you need 2D apertures, either physical or virtual, which will give you both azimuth and elevation, right? So this is one of the main problems, right? And of course, the other point is that, why do we all have cameras? It's because we all understand the natural image, right? There's no immediate perception. If I showed you a radar image, like I started to show you, understanding what it is not easy. What's in there, right? The information content from the TFT images that you see is not really interpretable. So anyway, let's move on. Okay. So the other thing is this: compared to LiDAR, the kind of point clouds that you get from a radar processing. So when I say a radar processing point cloud, straightforward. You take the IQ, you do the processing. It's a sequence of FFTs. As a matter of fact, I only showed you 2 FFTs, one for range, one for velocity. I'm going to add a third for angle. Okay? Then I'm going to repeat this in time. So actually, if you look at it, the tradition, all the information that comes out of one of these receivers is range, Doppler, velocity, angle, time. So 4D data here, right? And now you have all the information that you want, and you can process this to your heart's content. Right? Processing this creates the point cloud, okay, for the radar. And the radar point cloud compared to the LiDAR point cloud, resolution-wise is much.
Just the thought that they provided. Is it possible to tailor cars so to use the sound that they did to figure out where they are?
Sure, as I said, so as an assist to this, but acoustics will be much less, resolution-wise, much less bandwidth, etc. Remember, what this is going for it is this huge amount of bandwidth that you have. Okay, so remember, if you want to use something, it has to be the same order of magnitude to be able to, improve on this, right? So, so it's like this. So the rest of the talk is about looking at these cons. So essentially, the game with radar is, obviously, two things. Look at what the radar's limits are and try to work around it. That's the. So how do you work around and improve it? You clearly have assistive things, right? And as I said, I will show you our approach to this thing is, as everybody in the industry does, is to use a camera. Right? So it's a camera plus something, right? And that plus something could be either LiDAR or radar, right? And the second is, since the radar has these limitations on angular resolution, how the heck can we work around it? Are there some, workarounds on the angular resolution from a fundamental radar processing perspective, right? Okay. So the short answer is, the rest of the talk, I will point out that, again, we have borrowed heavily from what signal processing comms people learn from other domains. And one is called, so in this, the TI, hardware, they basically, have what's called a cascading, right? So they essentially take a base design and they replicate it, they cascade it. And now you get what 192 element, you can get a virtual 190. So I will show you how you create a virtual MIMO array much larger than your physical array. So it pretends to be a much bigger aperture, right? So the whole game is this: you have a small physical aperture. How can I, operationally make it look much larger? So you can create what's called virtual MIMO, and there's another way, which is using synthetic aperture. So I don't know if any of you have known what synthetic aperture is, but when your airplanes fly around, and you do remote sensing, they have a side-looking radar, which looks, side-looking and downwards, right? In order to image the Earth, right? And it uses a principle called synthetic aperture. So again, the physical aperture is small, but because of the motion on the plane, which is the same thing you can exploit here, you can, if you are able to maintain coherence over a coherent processing interval, get a much larger synthetic. So you get a virtual MIMO synthetic aperture, and you may be able to combine them together to basically try to get around this. All right. So essentially, and then finally, I think the third point I would like to make is the following, right? I said to you that the total sort of information is range, velocity, angle, and time. We often tend to ignore that, when you're looking at a scene, right? So let's say I cannot, I have too many objects in the same range bin. I cannot resolve them in range. Then what do you do? Let's look at velocity, right? So a pedestrian versus, a cyclist or another moving object, right? You may possibly be able to, discriminate in velocity. Well, let's suppose that's also not possible. And clearly, as with our eyes with a camera, maybe you're able to discriminate in angle, right? They are in different, angular, azimuth. And then finally, none of those occur in a static image. So these three, you can insert as an image. You look at a frame. Because, as I said, when you look at you look at objects over time, right? All of us, let's say a human being, let's say, you're imaging a pedestrian. Let's say you're imaging a pedestrian versus an animal, right? The gait, the motion we are all extended objects. In any of these high resolution, we come across as point clouds, right? Maybe in one frame, I can't detect that this is a human being versus an animal. But if I look at multiple frames, okay, and let's look at the Doppler profile, or what's called micro Doppler, of the way I walk and what my arms and legs motion, which allows somebody to determine that this is a human walking versus a dog or a cat walking, right? So the point is this: there's a lot of information in these multiple domains that can and should be used for object classification, right? So maybe even, so depending on, as I said, the whole idea is this, that you can start with this sort of basic hardware, basic processing, and then you can, try to use your, your smarts and the new tools based on AI, ML, neural nets, etc., to explore how I can fuse different aspects of this 4D data plane that I have. So again, range, velocity, angle, and touch. Okay? In order to exploit, all of these, of course. What's the no free lunch? Complete. Okay, none of this is going to come free, right? I will point out to you, right? So as always, you can go down a path of processing, but then you have to pay the piper. And then you have to figure out that if I want to do this in real time, if I get a grand solution, how do I manage the compute so that it can get, done in our local process. All of this was done offline. Right? You can get all the data, I'll process it all offline to show you what the limits of the possible are. If you want to do this real time, it's a different. All right, so I'm going to just skip through this. So as I said, this radar resolution ultimately, focuses on things like, can I get more antennas, right? Okay. And this is through cascading, right? This is the TI solution, right? NXP has, a different solution. They actually want to do so some combination of improving physical aperture, then doing virtual MIMO, then adding on signal processing, right? All of this, right? Okay. And, so these are all sort of, ways in which people are looking at, and then over time, process over time, right? All of this is, okay. So just to give you a sense that, look, so I'll tell you, I'll think what, 10 more minutes? Yeah, 15. All right. I'll go through this example. So we created our own, CNN-based radar. So I'll just give you the ideas behind that. And then if I have a few minutes, I'll talk about the MIMO, the SAR, synthetic aperture with MIMO using this cascaded radar. So the whole idea is that, with a camera image, of your computer vision friends are able to do this, eyes closed with YOLO or something, right? Whereas, you get this thing on a LiDAR cloud, and the radar cloud is even worse, right? Okay, so you have to work hard in order to do, say, simple things like object. I mean, this is very good, right? This LiDAR thing is very good. Radar is not, right? To do object recognition, right? So the whole idea is this, that, as I said, so suppose, objects are not the same. So if you look at a human being walking, so as a matter of fact, this is not terribly new. Look, this idea of exploiting micro Doppler because of the human gait, right? So if you can look at it, right, a classical walking human, you obtain this short-time Fourier transform, and you see different parts of their bodies have different signatures, right? So if you're able to have the whole idea of this in your foregator, you're able to have point clouds in which you're able to discriminate. You have multiple points, and the clusters of those points have different signatures, right? You should be able to determine that this is a human being versus a dog or a horse or something else, right? So there's much more information rather than just looking at it as a single point, right? Because it's a cluster of points. And as a matter of fact, you can see this. So this is, by the way, we have a whole bunch of data sets, some of which we have made public. I'm happy to share more. So this is taken, at the University of Washington. And what do you know of Washington? It rains all the time, right? So you have clouds all over. It's cloudy and rainy all the time. So we have perfect experience for taking a lot of challenging data sets, right? So this is in our parking lot. Okay, we have pedestrians, cars, somebody on the side. Okay? The whole point is you can look at the velocity versus time. So again, versus time, the signature. right? The whole idea is to show you that there is significant information if you're able to capture time. So our radar net is we take the raw data, IQ, and then I showed you one with two FFTs. Now you have a range FFT and velocity Doppler FFT and an angle FFT, right? Post that, what we are going to do is we would push this post FFT, and FFTs are information preserved. And up to that, right? There's no loss of information. It's all linear processing. You have all the information that you get the IQ. Now, post that, you can now go to town figuring out, how to generate the point clouds, right? Moment you generate the point clouds, there you're doing some of these nonlinear processing. Okay? You're throwing in your ML approach, etc. So our idea is the following, right? And this is, you will see, what we wanted to do was this, processing 3D or a sequence of 3D, which would be 4D, is only feasible, on a cloud or something, right? On your offline town, right? And you are trying to find something that you could be moved to, closer to real time. So the idea here was this, that a lot of the information we have are available in lower dimensional class. So for example, depending on the kind of objects and the, maybe the information in the velocity class, okay. So if I have the 3 dimensions, range, velocity, and angle, you have 3 2D class. You have range and velocity, range and angle, velocity and angle, right? And then we can, cascade them over time, and maybe, 1 or 2 of them suffices to do the discrimination. So this was basically the idea. So we have these three-dimensional FFTs, okay? And now we're going to start taking cuts of this, right? Out of the 3D cube, right? So, and as I said, in reality, you have the 3D and then time, and you have, multiple, frames, which are this 4D perspective, right? So this is our radar. And the point I was going to make is this, that after you go through all of this, I'm going to skip this data augmentation part. We can do this offline. These are all the usual tricks you do, not to do overfitting, to include, things like symmetry, translation, low level stuff. So I'm going to skip that, right? And now see what happens. This is now, we divide this into 3 parallel branches. Right? Each one is a 2D section of the 3D, right? So you have a range, angle, sequence. You have a range, velocity, angle, and each of them is processed through a CNN, autoencoder sequence, right? And then, of course, after that, after you do the split, this is largely because to keep the computation down, I have enough few steps. Right? I'm going to tell you what the whole idea is. And then, finally, as I mentioned, this, remember, the use of the radar is to show its worth when, as I said, if, when the scenario is challenged, right? You're not going to use this when it's a beautiful, bright day. Your camera works just fine to do all the, object recognition, right? Yeah.
Yeah. So is the benefit here of taking these cuts and then identifying feature across the cuts compared to processing the 3D is only at computation level, or do you get performance benefit too?
Mostly computation. You're giving up some performance, but you're winning largely on the computation.
But if you train your model offline and you're doing inference in real time, why do you care about computation?
So here, again, everything is offline. So even the inference, etc., is offline. Sure. So let me tell you this. So let me just give you the scenarios, right? Whoops. Run ahead. Okay, so here's the actual list, right? So this is a part of our data set, right? So what you have is you get a lot of data and perfect weather type of data, right? The point is that we really want to test this. So the radar, after you train the radar with camera as a super, so you train all this model, with the camera, right? And you use it, to set, the radar's, parameters. And then the results we are going to report are all radar only in these difficult circuits. Nighttime scenario. So the testing is all the scenarios with the camera is used. Okay. Hopefully that, and then to answer your question, directly. So this is sort of the results in terms of precision and recall compared to other algorithms, right, with this training. But I think the thing is what is the time complexity, right? So this is a sort of the complexity of the memory needed for the algorithm. And then you can see that there are very significant, if, for example, I did a complete 4D, right? So this is the number of flops that you'd require, and this would be about 2 orders of magnitude, in order to run. Okay. Similarly, in terms of memory. So the wins here are largely in terms of, right? In terms of performance, if you see this, right? This is, our algorithm, right? Overall, this is what we are getting, 84. And obviously the parking lot, it's pretty close to perfect. The hardest is this, the nighttime for road signal, right? So it's nowhere close to being up. But it's, these are, so what, like everything, you compare it to other competitive, approaches, and we clearly can outperform. So just to answer your question. Right? So to give you more details on this, right? The whole idea is this, that again, the reason to fuse it is because there's redundancy in, so in order to do a discrimination between, one object and another, the information could be both in velocity and angle, right? So both fusing, say, the range velocity and the velocity angle information is useful, right? Et cetera, et cetera. So this is the reason to fuse it, and I'll tell you how we do this. So essentially, is this clear? So the point is, the taking the 3D plus time, which is 4D, and reducing this to a sequence of parallel 2D plus time, right? And then fuse, computing on those, doing all your CNN on those, and then fusing it seems to be a, for us seems to be a workable trick. Any quick questions? So I have like 5 minutes. I just wanted to talk about my more SAR work. Hello. Right. So again, this is so just I go back to the base problem of angle resolution, right? So I mean, in a camera vehicle or in a LiDAR vehicle, angular resolution seems like a solved problem. But it's not so with radar, right? So as I said, again, for signal processing comms people, there's a long history of angular angle over rifle, okay, 30, 40 years, right? What's the problem? You can't apply that. The point is, this has been actually known. These are model-based approaches, and they are very sensitive to the model exceptions. And I'll tell you what, one of the major things that is very sensitive to is this resolution issue, right? So if you tell one of these are called super resolution. If you go back to the 80s or 90s, there are tons of papers called angular super resolution, right? So when they say super resolution, it's resolution higher than what you would do with FFT-based processing, right? FFT, okay. So you can do better than FFTs, but you can do it if you told this algorithm how many targets they are you do. If you don't tell them how many targets you're looking for, they usually many times they crash it. They incorrectly estimate the number of targets. Now, as you know, in your scenario, the first thing you don't know is how many targets there are. That's what we started out with, right? So these are notoriously what we call sensitive, very model sensitive, and it has these inputs that you need to decide. So these don't work very well. So the two, again, what I would like to say, the two main approaches was, how do I get more MIMO then? So as I said, virtual MIMO that the TI chip enables, and synthetic aperture. So if you look at synthetic aperture, this is just the analog of what I call how synthetic SAR was developed, but for airborne windows, right? Except that you now have, as I said, in order to do coherent processing, the thing that you need to know is your own self trajectory. Okay? So you need to, in order to synthesize this aperture, you need to know what your trajectory is. So how do you know what your trajectory is? Okay. So this is, in other areas, it's called simultaneous look. You have to localize yourself. This is called an ego in the radar sort of word. It's called an ego motion estimation. You need to know, where you are pretty accurately. Okay. As you lose accuracy, errors accumulate, and the coherence interval, degrades, etc. leads to. But anyway, so this is one. Okay. So as the car moves, that so you basically get, particularly as you said in cross trains, much higher resolution. I'm going to skip all this. This is a lot of math in order to show you how. Okay. And this again requires very significant. In order, to do this coherent processing, the star, just like the other stuff, it has significant computing. So, a cheaper alternative, which is why, is the TDM MIMO approach. So, if you say, I have multiple ways to increase the limited physical aperture to a much wider, virtual aperture. One is star, but that has a lot of algorithmic complexity. Complexity-wise, the cheaper thing would be to do TDM MIMO. Okay, there's much lower complexity, right? And you can, sort of get the gains out of this, right? So anyway, what I was going to show is that I don't have applications of our method to actual data. So the results here are only based on MATLAB, right? So, but I think this is again, again, if you design this well, the short answer is you can improve, clearly, as you said, from 15 degrees, down to a few degrees, which is what the goal is, right? That you're able to get a beam, which is, if you look ahead, it's in your lane, it doesn't, you can, discriminate a vehicle in your lane.
So how does it affect if the target is moving? Will have to be static or it can be.
So great question. So this star, your platform moves and the target is static, right? So this is, So now again, if the target moves, this can be adapted, but you have to redo this, So if you have a solution which works for a period when you can assume that the target is in the same bin, resolution bin, if the target doesn't satisfy that, you have to redo that. So you can start with this, see for what range of targets is, for the coherent processing that you need, is a target in one bin. And if it starts to get violated, then you have to go. Okay. All right. So again, these are all, I'm going to skip all this, right? So by the way, there's a very nice MATLAB toolbox which allows you to simulate, you can simulate in this, you can simulate a vehicular scenario, right? And you can get this MIMO summit method. So you can actually do this, right? You can put a car, you can have a lane, right? Or you can, and you can have so for example, you can simulate this. You can have a car in one lane and you can have other vehicles in the next lane, right? And you can see with the side looking radar, what, resolution you get. Can I detect? Okay? Based on this sort of, radar and maps, can I detect? So one of the things I mentioned was that I didn't show you. This is our setup. So we have this chassis where you take that, the cascaded board, okay, with 2 TXs and 4 RXs, right? And which you can use. Sorry, this is the original board, and then you can use the cascaded board. You can stick it, So we put this on our on a car, and we drove around to get all this other. The images that we have, and it's looking sideways, right? In order to get be able to synthesize this synthetic aperture. So anyway, so I'm going to skip a lot of this, but essentially you can get range angle maps, right? Yeah. Okay, so because if you're looking sideways, you're looking to see what you can see in the next lanes, and you're looking to see anything. Okay. So you can see this, right? So you can have this simulation. And we actually tried this on some real data. So we had parked cars, right? You can see this is car 1, car 2. This is background from the static parts of it. Really, by the way, we have some other work in which you're trying to do background. Very often, given that most of the objects of interest are closer and mobile, and most of the background stuff is not of interest. In order to detect the smaller objects with a weaker radar return profile in the presence of stronger backgrounds, you have to do some background separate piece of work. Okay, so you have these range angle, or range. So they are different maps, right? So this is the sort of the idea is to say that, you have a range azimuth map or you have a range, angle map, right? And if you compare to this, if you use MIMO-SAR, you can see the ability for improved object detection. All right. You can virtually, have no detectability from this sort of, radar maps, right? Whereas from MIMO-SAR, you can start to see outlines that are trainable. So that's the whole point, right? This is applied to these sort of images and taken, right? As opposed to the range and MIMO-SAR. Okay, so hopefully you get an idea of what we've been up to. Okay, I'll over time. Thank you. Any questions?
Questions?
Yeah, I have a quick question. I know the azimuth angle resolution is pretty low, but even in the most advanced TI4, we get 1.2 degree on the thing. Azimuth.
By the way, did you try it? Because I haven't tried it.
I read a paper you mentioned that.
Yeah, so it would be good for somebody to verify.
We actually tried in our code here
Yeah.
where we fly the drone. We got about 5 to 6 degrees at most. Grass might be the one that was actually.
This thing,
Yeah.
background. Yeah, so I think it is one of the things is, if you remove the background, that's a lot of, maybe that helps you improve the.
Yeah, 1.2 degree, I think, is what TI advertises.
Advertises, yeah.
With their cascade, yes.
Yeah, for the high resolution, I think it's much more than angular, right? So I mean, if that's possible to put one radar in the horizontal angle and rotate to 90 degree and put another one in the vertical.
Yeah, but that's, this virtual, this thing, it's supposed to, so if you look at it, the 2 transmits are like this, the 4 receives are like that, all right? So the virtual MIMO array is supposed to be a filled-in 2D array. So you're right. I mean, if I want high resolution, it's very clear my array has to be in 2D, right? And it's supposed to be. So if you look at it, here, that's how in your TI board, here's how the transmit array looks, transmit and receive configuration looks like. Yeah, skipped it. But anyway, if you look at the transmitters are vertical.
Yeah,
Receivers are.
to the.
So it's supposed to, if you do the TD MIMO right, it fills in the 2x4 and gets you a 8 2D, and in 192 you're supposed to have a filled 2D.
Can we just map to the map one improve the sensitivity?
I don't understand the question.
It's like you get a 2D on this way and 2D on this way and map them together.
No, but when you say map them together, no, you're trying to get a 2D array, right? Because in order, so when you say angle, it's this and that, right?
Mhm.
You have 2 degree, two angles you're trying to estimate, right? As I said, azimuth is important in more of the scenarios, but there are scenarios in which you need elevation too. That's why. So if you didn't need elevation, you would focus purely on one thing, correct?
Mhm.
But you need, in order to, you need both. So that's why you need a 2D array. And then, with that 192, you're filling in a 2D array much more, densely. Right.
Does that mean the compute can happen parallelly or is there data dependency concerned?
No, here this one is in parallel.
Okay.
So what's happened is, we have divided, if you look at the architecture, this one can be parallel. So these are parallelized, and then there's a synthesis step. This So in your presentation, you focused on a lot about computational complexity. So as far as I know, 4-dimensional Fourier transform is very expensive. But like, so this is not 4. This is 3 1D, 1D, 1D. Then you're stacking together 4D. There's no 4D. So my question is that how difficult are topic? Like if I put a NVIDIA GPU based text will it work or like it's nearly impossible to do? No, it's no, computation. Look, you're right. We do FFTs on our lab. That's these questions. Can you do it in real? Remember that this is a control problem, right? I have to observe this, make a decision to take the next step. That loop is missing. Correct? The real-time mean is that this is not, to be done offline. It's to be done in real time. So that's obviously the goal. So in one sense, you pursue, optimal algorithms, but then they lead you to whatever, complexity factor. And then you have to pivot back to, doing all of these trade-offs, bargains that we do. I win more on the complexity and lose a little bit of performance, and then look at the architecture of the processors, etc., to support it. I'm not an expert in that segment.
I have a more generic question. Where do you see the standardization of this radar kind of devices going?
So I think
maybe we can talk about from IEEE technical groups.
I would say this, that, so this is interesting. So, if you look at this, it's always, as they say, old wine, new bottles. Right? A lot of research is, as they say, read, search, and, apply it to something else, correct? This is a very good example. As I say, that's why I gave this talk. I'm a comms person. I know this, like in my sleep, the multiple accesses thing. And then when you come to this radar problem, you see 0 papers, nobody, discussing this. Well, you know that this is going to be an issue. Right? And the big challenge is, so if you think, why do our cell phones work? Why do we, why does Wi-Fi? What's the answer? Forget the technical answer. The technical answer is enabled by standardization. So I don't know if any of you do, most of you are not comms people. You don't do comms research or Wi-Fi research, right? In my lab, I do that 80% of the time. In order to do credible comms research or cellular research, what do you have to do? You have to do like, we're going to give you a facile example. You all pay taxes. None of you have read the US tax code. You trust your accountant to enter the tax code and pay your taxes, right? We all use Wi-Fi, but you're not with the Wi-Fi standard, which is, I can show you, I have a free copy. It is about, few hundred pages long. And the cellular 5G standard is, there are multiple technical standards, each of them are 300 pages.
They're coming with a new version next year.
Which one?
Release 19.
Oh yeah, Wi-Fi is, cellular has this stack, like a tax code. Every year, 18 months, it has a new release. So none of us read that. And yet, if you want to do credible research and you say, my work is, it follows this, either way. My work follows the standard, which would be ideal if you get your hour in Hong Kong, right? Or my work breaks the standard, either way, right? You have to refer to that. You have to use that as your reference document. So we do it all the time. If you ask me a question about Wi-Fi, how does Wi-Fi work? Me and my students go to the standard and try to understand how some Mac program something works. So the short answer is this, that our wireless, all our networking devices work because, and by the way, the reason I know this is I work with Intel as a standards architect for 3 years. I don't know if you know this, that if you get employed in one of these companies, Qualcomm, Broadcom, any of the semiconductor companies which are doing standards, you will go to this international meeting held every, there's 3 + 3, 6 meetings. They're almost going to every 2 months. Going to a meeting where all of the world's best engineers working on that problem come. They yell at each other. Basically, standardization is competing ideas coming into a room. So, Samsung, Intel, name everybody, Qualcomm, Broadcom, Apple, right? Everyone's there. All their engineering leads are there. They, thrash it out. There is a proposal process, there is a voting process. So I can tell you how this works offline, right? the point is enormous amount of engineering time and talent goes into it, right? So, they don't get to write papers. They get to go to standards, produce IP. So, if you work at a big company, what would you be producing in this? You would produce patents, right? And you would go to standards to get your IP into standards, right? Given that's how, wireless technology works, this needs standardization. If things have to interoperate, you need standardization. So if, a Cisco access point has to work with, Broadcom chipset, Wi-Fi chipset, you need standardization. If an Ericsson base station has to work with a Samsung handset, you need standardization. And so the point is as these technologies integrate and you have interoperability, and interoperability can come around from many great perspectives. So I think, great question. I see no evidence of the car. As a matter of fact, let me tell you a failure. Have you heard of DSRC? It's called Dedicated Short Range Communications. It was an offshoot of Wi-Fi. So for this, FCC allocated 75 megahertz for 5.9 for vehicle-to-vehicle communications 30 years ago, called DSRC. At that point, it was assumed that cars would have Wi-Fi to communicate with each other for the same public safety anti-collision rules. Was never used. Okay, so the FCC got annoyed after a while. It gave the spectrum, no Ford motor. Do you have Wi-Fi in your car today? No. You have Bluetooth and things like that. But your car is not talking to another car using Wi-Fi, or car is not talking to a roadside unit using Wi-Fi, right? So this was given out 30 years ago. The FCC finally, by the way, they took it over. Right? There's always, if you say use it or lose it, because on one hand you say spectrum trans, on the other hand you give somebody spectrum and they don't use it, so you lose it, right? So my point is that this is a great example of technology, not matured, not used, because they didn't, sit around and, so actually a standard release, this was not an example. There's an 802.11p standard, right? Correct. No vendor actually. So first of all, so I would say there are two steps. First of all, there has to be standardization. And second of all, a vendor, a marketplace has to see that there is somebody who's willing to, pay for it, integrate it into the products. But but this is a great point. And I think that from a national perspective, there needs to be leadership. Whether it comes from NSF, and from IEEE. I think honestly, IEEE should stop saying to people, write 300 more papers. More papers, and actually focus on improving technology. And, these problems are really required. Lots of, so as I said, standardization, what you see is the result of the best minds and engineers coming together and working for each standard takes 12 months, 18 months. If you ever become a standard engineer, that's what you will do. You will go to 6 meetings a year. You will be arguing with, if you're representing whatever company X, you'll be arguing with everybody else about your ideas to solve that problem. Okay, and the sort of the best and brave, they come together, they get standardized, and that's anyway.
Okay, any other questions? Yes.
Yeah.
I was going to ask 2 questions. The first, the experiments you did on the experiments that were done in the parking lot, because I read that paper actually.
Okay.
Last week. What frequency were you reading at when you trained the model? The second question is that
77 to 80, all the same. Yeah. Exactly.
And the second question is, for example, in IROS, to presented their radar technology and their autonomous driving, or at least their crash detection, which really is. I tried it myself. I almost crashed. It's too sensitive.
Okay.
Have they attempted to do any standardization? Because,
as I said, I asked my first question was to TI. At the end of the day, you see in this business that we have sys and integrators, but they only depend on 2 or 3 vendors. I was asking TI all the time that design came in Dallas. Are you guys pushing for some standardization so that if you sell to, whatever, Volkswagen and, all of this. Yeah, you could have when a Volkswagen is on the road with a Hyundai, but are you going to be able to do that? Answer is no. I don't think.
I know Volkswagen, but I asked my.
That's right, yeah.
She works between.
No standardization. As a matter of fact, this 822.11p flag. So, this is the DOT itself here was on this flag. So then Volkswagen and Toyota were on one side, and everybody else wanted 5G. So, at the end of the day, people said, why the heck would I want, 5G as a small cell technology is a competitor. If they can provide you, so this is the other big interest. I go back to the first statement maybe, right? As bandwidths, whether it's Wi-Fi or cellular, gets larger and larger. Can you do crude radar stuff, with radar-like stuff, which is localization with unmodified 5G or with unmodified Wi-Fi? The SOLI project from Google and others, right? So I think these questions are going to be entirely pertinent. Like if I can get halfway decent performance with unmodified or minorly modified commercial gear in indoor environments, etc., so I think that 811p was also an eye-opener because the vehicle manufacturers could never come to an agreement. To a standard agreement. Okay, we'll all back this and we'll go mature this and we'll get vendors to provide the chipsets, etc. With tablets.
All right, so I think we're running late for our next meeting. Let's give Professor Raya a quick one.